In July of 2005, a telescope in Chile caught something tearing through our solar system at over 150,000 miles per hour. It came from a direction no interstellar visitor had ever come from before, straight out of the galactic center. Scientists traced its path backward through the Milky Way and found it had been traveling for somewhere between 7 and 14 billion years. It carried chemistry that breaks our models of comet formation, and it was the third object like it we had spotted in less than 8 years. If you enjoy content like this, consider subscribing. We cover the discoveries most people don't hear about until it's too late to ignore them. That object was just the most visible piece of a larger pattern, because something has been disrupting star chains across the galaxy. An invisible mass punched a gap through a river of stars, and no known object caused it. Meanwhile, at the galactic core, 3 separate unexplained signals keep firing. Gamma rays, ionized gas, charged particles, and the leading explanation points to something we have never directly detected. And 2.5 million light-years away, a galaxy larger than our own is closing in. Its dark matter halo is already touching ours. This video is about all of it. The interstellar comet that arrived from the oldest part of the galaxy, the invisible forces tearing gaps in stellar streams, the glow at the heart of the Milky Way that may finally be the fingerprint of dark matter, and the approaching neighbor that may, or may not, end everything we know about our cosmic home. Prepare yourselves. We begin. On July 1st, 2005, a telescope in the Chilean desert caught something that should not have been there. The NASA-funded Atlas survey system, a global network built to hunt asteroids that could threaten Earth, flagged a moving object in the direction of the constellation Sagittarius. Within hours, astronomers pulled archival data from 3 other Atlas telescopes and the Zwicky Transient Facility at Palomar Observatory in California. They traced the object's path back to June 14th. And the moment they calculated its speed and trajectory, the situation became clear. This object had not come from our solar system. It had come from somewhere else entirely, and it had been traveling for a very long time to get here. The object was officially named 3I/Atlas, the third confirmed interstellar visitor ever recorded in human history. The 3I is straightforward. Third interstellar. The name is precise, but the reality behind it is staggering. Of all the directions it could have arrived from, this comet came from the direction of the galactic center, the oldest, densest, most chaotic region of the Milky Way. The previous 2 interstellar visitors came from the opposite side of the sky. This one came from inside. It was moving at over 150,000 miles per hour relative to our solar system. That speed alone rules out any origin here. Objects that form around a star and get gravitationally ejected can reach high velocities, but this object's speed and path could not have been produced by any planet or star in our solar system. No gravitational slingshot here could have given it that trajectory. The only explanation is that it arrived from interstellar space, having crossed an enormous stretch of the galaxy before entering our neighborhood. As astronomers gathered more observations, the picture grew stranger. Early estimates from the Vera C. Rubin Observatory placed the diameter of its nucleus at roughly 12 miles across, making it far larger than the 2 interstellar objects detected before it. Its coma, the cloud of gas and dust surrounding the core, had grown from roughly 8,000 miles wide to nearly 12,000 miles wide in the span of 11 days. The object was warming up. It was becoming more active, and it was heading toward the inner solar system, toward the region where Earth lives. It would pass its closest point to our star on October 30th, coming within about 130 million miles, just inside the orbit of Mars. It would make its closest approach to Earth in December, coming within about 168 million miles. Astronomers confirmed it posed no threat to our planet, but the distance was almost beside the point. What mattered was what this object carried with it, a record of the galaxy it had traveled through for billions of years. And that record, as scientists would soon discover, was deeply unusual. The chemistry in its coma did not match expectations. Its color was reddish, consistent with organic compounds cooked by cosmic radiation over immense timescales. And when spectroscopic instruments measured its emissions, they found something missing that should have been there. a detail that would point back toward the ancient, violent environment it came from. 3 interstellar objects in 8 years. After decades of watching empty skies, the galaxy was suddenly sending things our way, and scientists were beginning to ask whether that pattern was a coincidence, or whether it was telling us something about what is actually moving through the Milky Way right now. The answer to that question starts with where this object came from and how long it has been traveling to reach us. The direction matters more than it first appears. When astronomers traced 3I/Atlas backward through the sky, they found it arriving from the constellation Sagittarius, the direction that points toward the galactic center, toward the dense, ancient heart of the Milky Way. The previous interstellar objects, Oumuamua in 2017 and Borisov in 2019, came from the opposite direction, from a region of the sky near the solar apex. The direction our solar system is moving toward as it orbits the galaxy. Objects arriving from that direction can sometimes be explained by relative motion. Objects arriving from the galactic center are harder to account for. They are coming from a fundamentally different part of the Milky Way. The galactic center is not empty space. It is the most crowded, most energetic, most gravitationally extreme environment in the entire galaxy. Hundreds of millions of stars are packed into a region a few thousand light-years across. Massive molecular clouds, the birthplaces of stars, crowd together supernova explosions have been firing through that region for billions of years. And at the very center sits an object of enormous mass, generating gravitational forces that bend the paths of stars into tight, fast orbits that nothing else in the galaxy can produce. To have come from that direction, 3I/Atlas had to have originated in, or passed through, a region of the galaxy with a long and violent history, and the timeline confirmed it. A study published in July 2005, led by Matthew Hopkins and collaborators, estimated with 68% confidence that the comet is between 7.5 and 14 billion years old, based on the stellar populations typical of the region it came from. A separate independent analysis by Asta Taylor and Daryl Seligman placed its age between 3 and 11 billion years. Both estimates point to the same conclusion. This object is almost certainly older than our solar system, which formed 4.5 billion years ago. Think about what that means. While our planet was still forming, while the first continents were taking shape, while the chemistry of early life was just beginning to assemble, this object was already old. It had already been drifting through interstellar space for billions of years before Earth existed, and during that time it was exposed to everything the galaxy could throw at it. Scientists traced its trajectory back 10 million years using data on stellar positions and motions. A team led by Xavier Perez-Couto found that, during that period, 3I/Atlas may have passed within about 3 light-years of at least 25 known stars. A separate analysis suggested it likely belongs to the thin disk population of the Milky Way, the flattened region where most of the galaxy's younger stars live, and where star density is highest. That disk is full of gravitational influences. Stars pull on passing objects. Nebulae create drag. Close stellar encounters can change a trajectory significantly over millions of years. This comet has been shaped by all of it. Its surface has been bombarded by cosmic rays for an almost incomprehensible span of time. Its orbit has likely been altered by dozens of gravitational encounters we will never fully reconstruct. Its original home star is impossible to identify. It has been in transit long enough to have mixed into the general stellar population of the galaxy completely. What arrived at our solar system was not a fresh fragment from a nearby system. It was a relic from the deep past of the Milky Way, carrying chemistry forged in conditions that no longer exist, from a star that may no longer exist, shaped by forces spread across billions of years of galactic history. And when scientists looked closely at what it was made of, they found something that should not have been there, and something that should have been there, but was not. Comets have a chemical fingerprint. Scientists have studied hundreds of them in our solar system, around other stars, and over time, a consistent pattern has emerged. When a comet heats up near a star and begins outgassing, the vapor it releases follows certain ratios. Two metals in particular tend to appear together in roughly equal amounts: nickel and iron. They are chemically linked in the kind of rocky, metallic material that makes up comet nuclei. When one appears, the other follows. In the coma of 3I/Atlas, nickel showed up clearly. Iron did not appear at all. The Very Large Telescope in Chile detected nickel vapor in the comet's coma on July the 20th, 2025. By that point, the comet was still more than 4 astronomical units from our star, roughly 4 times the Earth-star distance, and already releasing an estimated 4.5 grams of nickel per second. That detection alone was unusual. Nickel emission in comets is rare, and when it does appear, it is a signal of specific temperature conditions and surface chemistry. But the absence of iron was something different. That absence does not fit the standard picture of comet formation. What does its absence suggest? The honest answer is that scientists do not yet know. Several explanations have been proposed. One possibility is that the comet formed in an environment with a different elemental composition than our solar system. A star with a different metallicity, a different ratio of heavy elements in its original planetary disk. Another possibility is that billions of years of cosmic ray exposure and interstellar radiation have altered its surface chemistry in ways we do not fully understand. A third possibility is that the nickel is concentrated in specific surface compounds that outgaze easily at low temperatures, while iron compounds require more heat than the comet experienced during this flyby. What the observation confirms is simpler. This object is chemically distinct from anything we have seen before. The comet also showed cyanide gas in its coma, detected by the Very Large Telescope in August 2025. Cyanide emission is not unheard of in comets, but combined with the nickel without iron signature, it points to a surface environment that has a different history than any comet formed in our own system. Its color adds another layer. Spectroscopic measurements showed a distinctly reddish surface. That red coloring comes from a class of organic compounds called tholins, irradiated hydrocarbons that form when simple organic molecules are bombarded by radiation over very long periods. The same reddish coating appears on objects in the outer edges of our solar system, where radiation exposure is high and temperatures are extremely low. On 3I/Atlas, that coating has had potentially billions of years to develop. The surface of this comet is a record of radiation exposure on a timescale that dwarfs anything in our local neighborhood. Scientists are already calling this object a key probe of the galaxy's population of icy planetesimals, the building blocks of planets that orbit stars across the Milky Way. Because when a comet like this arrives, it brings chemistry from a star system we will never visit, from a formation process we cannot directly observe. Every measurement scientists take of its coma is a data point from another world that no telescope can reach directly. The chemistry tells us the comet is old, exposed, and built differently than what we know. But the deeper question is not what it is made of. The deeper question is how many more objects like it are currently crossing through the Milky Way without us ever knowing. Because scientists have begun to calculate that number, and the result changes the picture of our galaxy completely. 3 interstellar objects in 8 years sounds like a lot. It is almost nothing. Scientists have run the calculations. Based on the detection rates from current telescopes, the sensitivity of those instruments, the known volume of space they can monitor, and the typical speeds and sizes of objects that can actually be spotted, researchers estimate there may be as many as 10 septillion interstellar objects currently drifting through the Milky Way. That is the number 10, followed by 24 zeros. Most of them are small. Most of them will never come close to any star system. Most will drift through interstellar space for billions of years, without interacting with anything. But here is what that number means in practical terms. A meaningful number of interstellar objects likely pass through our solar system every single year. Most go undetected because they are too small or too dark, or moving at the wrong angle relative to our telescopes. The 3 objects we have confirmed, Oumuamua in 2017, Borisov in 2019, 3I/Atlas in 2025, are the ones that happen to be large enough, bright enough, and positioned correctly for the instruments we had at the time to catch them. The Atlas system, the Vera C. Rubin Observatory, the Zwicky Transient Facility. These are powerful tools, but they are covering a tiny fraction of the relevant sky at any moment. One researcher at the University of Hawaii put it plainly: quite a few interstellar objects come through our inner solar system each year, although 3I/Atlas is by far the largest detected so far. The largest. Detected, both qualifications matter. The objects we have not detected may be smaller. They may be darker, rocky rather than icy, producing no coma to signal their presence. They may arrive at angles that place them against the bright background of the galactic plane, where the density of stars makes individual fast-moving objects extremely hard to isolate. 3I/Atlas was spotted moving right through the Milky Way's dense star field, and astronomers noted it was particularly difficult to track against that background. Oumuamua presented a different problem. It was not detected until it was already leaving. By the time scientists confirmed its interstellar origin, it had already passed its closest approach to our star and was accelerating outward. There was no time to launch a mission, no time to gather more than a fraction of the observations scientists wanted. A group called Project Lyra assessed whether a spacecraft could theoretically be sent to catch up with Oumuamua, which by then was already beyond Neptune's orbit. They concluded it was technically possible, but extremely challenging given the object's speed and head start. With 3I/Atlas, scientists had more time, but still not enough to do everything they wanted. The comet was visible to ground-based telescopes from July through September, before passing too close to our star to observe. Instruments scrambled worldwide. The Very Large Telescope, the Gemini Observatory, the International Gemini Facility, the Vera-C, Rubin Observatory, and even ESA's ExoMars Trace Gas Orbiter, which captured images from Mars orbit on October 3, 2022. The Mars Reconnaissance Orbiter also photographed it during closest approach. All of that effort for one object, for a few months of observation, and it is almost certainly one of thousands passing through while we watch. The galaxy is not a quiet place. Things are moving through it constantly. Most of them we will never see. But the ones we can see are now beginning to reveal something important about the structure of the Milky Way itself, and about what invisible forces have been shaping it from the inside. Somewhere in the outer halo of the Milky Way, there is a chain of stars moving together in a long, curving arc. Astronomers call it the GD1 stellar stream. It formed billions of years ago when a compact cluster of stars was gradually pulled apart by the tidal forces of the galaxy as it orbited. The stars spread out into a thin trail, like a string of lights stretched across the sky. They share the same velocity, the same trajectory, the same origin. They have been moving together for so long that their positions trace a smooth, predictable line. Except for one section. In the middle of that stream, there is a gap. The gap is not subtle. It is a clean disruption, a section of the stream where stars that should be present are missing, as if something swept through and scattered them. For years, astronomers tried to explain it using known objects. Could a large globular cluster have passed through the stream and gravitationally kicked the stars apart? No known cluster had the right trajectory. Could one of the Milky Way's known satellite galaxies have caused it? The orbits did not match. Every known massive object in the galaxy was checked, and none of them could have produced that specific gap at that specific location. A team from the University of California recently proposed the most credible explanation. A subhalo of dark matter, an invisible clump of mass moving through the Milky Way's outer regions, passed through the stream and disrupted it gravitationally. The team's leader, Hai-Bo Yu, published this analysis in 2005. The proposal fits the observation. But there is a complication. For a dark matter subhalo to have caused that gap, it would need to be denser than anything our best current model of the universe predicts should exist at that scale. The standard cosmological model, called lambda-cold dark matter, predicts that dark matter clumps at smaller scales should be relatively smooth and spread out. A subhalo dense enough to carve a visible gap in a stellar stream would require dark matter that behaves differently than the standard model assumes. Specifically, it would require dark matter that interacts with itself, a property the current model does not include. Physicists call this self-interacting dark matter, and it has been debated for years as a possible fix to several puzzles in cosmology. The GD1 gap may be one of the clearest observational cases yet for why that property matters. What stellar streams offer is something rare, a physical record of gravitational forces that acted on the galaxy in the past. The stars in a stream retain the memory of any force that disturbed them. Their spread, their shape, the angles of their positions. All of these encode information about what pushed or pulled them. Think of the stream as a seismograph for the invisible mass inside the Milky Way. When something massive moves through, the stream bends. When that something is invisible to every telescope, the bending is the only evidence it was ever there. This is why the discovery of dozens of additional hidden stellar streams in 2025, found using a new algorithm called StarStream, applied to data from the European Space Agency's Gaia spacecraft, raised immediate questions. Many of the newly found streams had unexpected shapes, wider than theory predicted, shorter, and misaligned with the orbits of their parent clusters. That misalignment is a fingerprint of external forces that should not have been strong enough to produce it. Something has been moving through the Milky Way's outer regions and leaving marks on the structure of the galaxy itself. The gap in GD1 is one mark, the misshapen streams are others, and they are all pointing toward the same question. What is moving through the outer halo of this galaxy, invisible to every instrument we have, and how dense is it? For decades, the working assumption was that dark matter in the Milky Way is spread smoothly through a large, roughly spherical region surrounding the visible galaxy. That region is called the dark matter halo. The model was mathematically clean. The halo is symmetrical, its density peaks at the center, and it tapers off gradually as you move outward. Galaxies form inside these halos. Stars orbit within them, and the whole structure holds together because of the invisible mass pressing inward from all sides. That picture is now significantly more complicated. Several converging lines of evidence are forcing scientists to rethink the structure of dark matter inside and around the Milky Way. The stellar stream gaps suggest dense subhalos moving through regions where the smooth model does not predict them. New simulations of the galaxy's formation history suggest the inner halo is not spherical at all. And some models now raise the possibility that the densest concentration of dark matter in the entire galaxy, the mass sitting at its very center, may not be a discrete object embedded in the halo, but rather a continuous part of the halo itself. The Johns Hopkins team published research in October 2025, addressing the glow at the galactic center, a persistent excess of gamma rays that the Fermi Gamma Ray Space Telescope has been detecting for years. Standard astrophysical explanations, including large populations of rapidly spinning dead stars called millisecond pulsars, have struggled to fully account for the signal's shape and spread. The Hopkins team, working with a system of simulations called Hestia, rebuilt the Milky Way's formation history from scratch, tracing its collisions with smaller galaxies, its mergers, its turbulent early phase, and found something important. When those historical collisions were included, the dark matter at the galaxy's core took on a different shape than earlier smooth models predicted. It became lopsided, distorted, and non-spherical. And that distorted shape, when scientists ran the math, produced a pattern of gamma rays that matched the observed signal far more closely than the smooth halo model ever did. This finding does not prove dark matter is producing the glow. Millisecond pulsars remain a competing explanation, and the debate is ongoing. But the research establishes something significant. The Milky Way's violent past left fingerprints on where dark matter is concentrated today. And those fingerprints look different from what any clean, smooth model would predict. A separate study published in early 2026 took this further. A team led by Valentina Crespi of the Institute of Astrophysics La Plata proposed that the dense central concentration of dark matter may be continuous with the galaxy's outer halo, forming a single unbroken structure that transitions from spread out and diffuse at large distances to extremely compact at the center. In their model, the supermassive black hole and the dark matter halo are not two separate objects. They are two expressions of the same mass distribution. The implications are significant. If the halo is not smooth, the subhalos moving through it are not anomalies. They are expected features of a structure that has been actively disturbed by the Milky Way's entire collision history. The galaxy has not been sitting quietly. It has been swallowing smaller systems for billions of years, and every one of those collisions left a mark on where the dark matter ended up. Those marks are now being found, and the clearest, most persistent mark of all is the one glowing at the very center of the galaxy. At the core of the Milky Way, three signals have been firing for years. None of them have been fully explained, and they keep pointing in the same direction. The first signal is a sharp spike of gamma rays at a specific energy level called the 511 keV emission line. This signal comes from positrons, positively charged electrons, annihilating when they collide with regular electrons. The annihilation releases energy at a very precise wavelength, and the European Space Agency's Integral Space Telescope spent years mapping where that energy was coming from. The result was striking. It concentrates heavily toward the galactic center, far more than any known population of stars or stellar explosions can account for. The second signal is a broader gamma ray emission at higher energies, the 2 MeV gamma ray continuum, also concentrated in the inner galaxy. The third is elevated ionization of molecular gas in a dense region near the galactic core, called the central molecular zone. Something is pumping energy into that gas at a rate that stellar winds and supernovae alone cannot explain. Each of these signals has been studied independently for years. Explanations involving pulsars, stellar explosions, cosmic ray interactions, and other known astrophysical processes have been proposed and partially tested. None of them comfortably explains all three signals simultaneously with a single physical mechanism. In 2026, a team of researchers, including Dr. Shyam Balaji of King's College London, published a study in the astrophysical journal Letters, showing that a specific form of dark matter, called excited dark matter, could explain all three signals at once. The mechanism works like this. Dark matter particles collide with each other in the dense central region. The collision briefly stores extra energy in what physicists describe as an excited state. When that energy is released, it produces positrons. Those positrons travel through the galaxy, eventually annihilating with electrons, producing the 511 keV signal. The higher energy gamma rays and the ionized gas in the central molecular zone emerge naturally from the same process. One mechanism, three confirmed anomalous signals. A match. This does not confirm that dark matter is responsible. The researchers are careful to say that. The study demonstrates that excited dark matter is consistent with all three signals simultaneously, which no other single mechanism has managed. That consistency matters because it is exactly the kind of test physicists use to narrow down candidates. When one explanation fits multiple independent observations at once, it earns serious attention. What makes the galactic center the right place for this process to operate is density. The central region of the Milky Way packs more dark matter into a smaller space than anywhere else in the galaxy. When dark matter particles are denser, collisions between them are more frequent. More collisions mean more excited states, more positrons, more gamma rays. The signal should be strongest at the center, and it is. The galaxy has been sending out these three signals for as long as our instruments have been sensitive enough to detect them. They are not random noise. They are structured, consistent, and concentrated in a way that follows the expected density profile of something massive sitting invisibly at the core of the Milky Way. That something is about to become even more difficult to define. For decades, the answer seemed settled. At the center of the Milky Way sits a supermassive black hole, a region of such extreme density that nothing, not even light, can escape. Scientists named it Sagittarius A star. Its existence was inferred from watching stars near the galactic center move in tight, fast orbits that no other force could produce. A group of stars called the S stars race around the central point in paths that require an enormous concentration of mass packed into a very small region. The numbers work out to a mass of roughly 4 million times that of our star. In 2019, the Event Horizon Telescope collaboration produced an image of Sagittarius A star, a shadow surrounded by a ring of glowing gas. The image matched the theoretical prediction for a black hole of that mass. It seemed definitive. A new study published in early 2006 challenges that interpretation carefully and specifically. A team led by Valentina Crespi of the Institute of Astrophysics, La Plata, proposed that the central mass could be an extremely dense concentration of dark matter made of particles called fermions, lightweight subatomic particles that follow specific quantum mechanical rules about how densely they can be packed. In their model, this fermionic dark matter forms a compact core surrounded by a broader halo that extends outward through the galaxy. The core is dense enough to bend light so strongly that it produces a dark central region surrounded by a bright ring, nearly identical to the shadow seen in the Event Horizon Telescope image. A separate related study demonstrated in 2004 that this kind of dense dark matter core can produce a shadow feature that closely resembles the image. The researchers point out that the core would be invisible like a black hole because dark matter does not interact with light. The two objects, a black hole and an ultra-dense dark matter core, would look nearly the same from the outside. What separates them, in this model, is continuity. A black hole is a discrete object embedded in the surrounding galaxy. The fermionic dark matter structure the team proposes is not separate from the galaxy's halo. It is the densest inner region of that same continuous structure. In their words, the supermassive central object and the galaxy's dark matter halo are two manifestations of the same continuous substance. This idea does not disprove the existence of a black hole at the galactic center. The researchers acknowledge that clearly. What it does is show that the current observational evidence, the star orbits, the gamma-ray signals, the Event Horizon Telescope shadow, is consistent with a different interpretation, and that alternative interpretation connects naturally to the other anomalies. The positron excess, the ionized gas, the three unexplained signals from the core that a single dark matter mechanism may explain. The S-stars still orbit something of enormous mass. That mass is real. What it is made of remains, as of 2026, an open question in a way that it was not considered open just a few years ago. The object at the heart of the galaxy is still there. Scientists are now less certain than before about what it actually is. And the deeper implication is even more striking. Because if the central mass and the outer halo are part of the same structure, then the dark matter surrounding the Milky Way is not just a passive cloud holding the galaxy together. It is an active, continuous, structured entity that reaches from the very center of the galaxy all the way to its outermost edges. And that entity is embedded in something even larger. Pull back far enough from the Milky Way, and something unexpected comes into view. The galaxy does not sit alone in empty space. It belongs to a collection of galaxies called the Local Group, a cluster that includes the Milky Way, the Andromeda Galaxy, dozens of smaller satellite galaxies, and the invisible dark matter surrounding all of them. For decades, astronomers have struggled to explain the motions of galaxies just outside the Local Group. Most galaxies in the universe are moving away from each other as space expands, but the ones just beyond our local cluster have been moving in ways that do not fit the simple expansion picture cleanly. Some move too slowly outward. Some appear to be getting pulled in directions that the Local Group's known mass cannot account for. A research team led by Ewan Wempe of the Kaptein Institute in Groningen, working with collaborators from Germany, France, and Sweden, published their findings in Nature Astronomy in early 2006. Using powerful simulations that evolved the universe forward from the earliest detectable patterns in the cosmic microwave background, the faint afterglow of the Big Bang, they found that the mass distribution just beyond the Local Group must be organized in a flat, extended plane, not a sphere, a sheet, a vast flat structure of dark matter stretching tens of millions of light years, with large voids above and below it. The Milky Way is embedded inside this sheet. This matters for understanding galaxy motions because the sheet exerts gravitational forces along its plane that partially cancel the inward pull of the Local Group for galaxies sitting within it. Galaxies in the voids above and below the sheet are simply absent. There are no galaxies there to be pulled in or pushed out. The result is a velocity pattern for surrounding galaxies that matches observations far more cleanly than any previous model. The researchers describe this as the first assessment of the distribution and velocity of dark matter in the region directly surrounding the Local Group. The discovery means the Milky Way is not floating in a uniform environment. It is embedded in a specific large-scale structure, a gravitational landscape that channels mass, shapes galaxy orbits, and determines which direction the future of the Local Group evolves. The sheet's dark matter is not the same as the Milky Way's own dark matter halo. It is the broader cosmic environment that the entire galaxy exists within. The halo surrounds the galaxy. The sheet surrounds the halo. This layered structure changes how scientists think about what is moving toward the Milky Way, because a galaxy sitting inside a flat sheet of dark matter is not approaching from empty space. It is moving along a corridor defined by the mass distribution of that sheet. And Andromeda, the largest approaching object in the known history of our galaxy, is doing exactly that. Andromeda is currently 2.5 million light-years away. Its dark matter halo, containing roughly 1 trillion times the mass of our star, is already overlapping with the Milky Way's own halo. The two halos are not approaching each other. They are already touching. The galaxies inside them still have distance between them, but the invisible structures surrounding those galaxies have already made contact. What happens next is the most significant unresolved question in the future history of our galaxy. Andromeda has been moving toward us for as long as astronomers have been able to measure its motion. As far back as 1912, astronomer Vesto Slipher detected that Andromeda's light was blue-shifted, meaning it was moving toward Earth rather than away. Every other galaxy in the sky shows redshift, the signature of cosmic expansion. Andromeda was the exception. It was heading straight for us. For over a century, the question was not whether Andromeda was approaching, but whether it would actually hit. In 2012, researchers using the Hubble Space Telescope measured Andromeda's sideways motion, the component of its velocity running across our line of sight, rather than directly toward us. With unprecedented precision, they found it was nearly zero, a galaxy with no significant sideways motion and a strong inward velocity is on a collision course. The 2012 analysis predicted a direct impact in roughly 4 to 5 billion years, with the two galaxies gradually merging into a single massive elliptical system over the following 2 billion years. The result seemed certain. Then new data arrived. A 2025 study, led by Till Sawala of the University of Helsinki, published in Nature Astronomy, incorporated the most recent observational data from both the Hubble Space Telescope and the European Space Agency's Gaia spacecraft. Gaia has spent over a decade mapping the positions and motions of billions of stars across the Milky Way and beyond, building a precision catalogue that was simply not available in 2012. When Sawala's team ran the updated numbers and accounted for the gravitational effects of the full local group, including Andromeda's large satellite galaxy M33 and the Milky Way satellite the Large Magellanic Cloud, the picture changed substantially. The probability of a direct collision dropped to approximately 50%. That number is not a slight revision. It is a fundamental shift in what scientists believe about the future of this galaxy. The reason is the Large Magellanic Cloud. That satellite galaxy orbits the Milky Way on a path that runs roughly perpendicular to the Milky Way Andromeda orbital plane. Its gravitational pull is displacing the Milky Way laterally, pulling it slightly sideways relative to Andromeda's approach vector. In roughly half the simulations the team ran, that displacement is enough to send the two galaxies on paths that carry them past each other, rather than through each other. In those scenarios, they separate by a distance of roughly 500,000 light-years or less. Close enough for intense tidal interaction, but not a merger. The remaining 50% of simulations still result in collision. And even a near miss at 500,000 light-years would be the most gravitationally violent event to affect the Milky Way in its entire history. The tidal forces at that distance would pull stars out of their orbits, stretch the disk of the galaxy, and trigger massive bursts of star formation. Andromeda is approaching at roughly 110 kilometers per second. Its dark matter halo is already in contact with ours, and whether the galaxies themselves collide in 4 billion years now depends on the gravitational nudge of a satellite galaxy that has only recently been recognized as a significant player in the local cosmic environment. The galaxy approaching us may or may not hit us directly. What it is already doing, at this moment, is pulling, and the question of what exactly is pulling back is becoming more complicated by the week. The Large Magellanic Cloud does not look dangerous. From the southern hemisphere, it appears as a faint, irregular smudge in the night sky, a satellite galaxy orbiting the Milky Way at a distance of roughly 160,000 light-years. For most of astronomical history, it was classified as a relatively minor object, one of several small companion galaxies drifting near the Milky Way. But over the past decade, a growing body of research has revealed that the Large Magellanic Cloud is far more massive than it appears, and that its gravitational influence on the Milky Way is significant enough to alter the galaxy's trajectory through the cosmos. The Large Magellanic Cloud arrived relatively recently in cosmic terms. Current models suggest it is on its first close approach to the Milky Way, having only entered the Milky Way's gravitational sphere of influence within the last billion years or so. Before that, it was drifting in a wider orbit around the local group. Its entry into the Milky Way's neighborhood brought a substantial amount of mass, and the gravitational wake it has created is still propagating through the galaxy today. One measurable consequence: the Milky Way itself has been displaced. When a massive satellite approaches a larger galaxy, the larger galaxy's center of mass shifts toward the incoming mass. The Milky Way's dark matter halo has been pulled slightly toward the Large Magellanic Cloud's position, creating what researchers call a gravitational wake, a region of enhanced mass density trailing behind the cloud as it moves. The actual center of the Milky Way's mass distribution is not quite where it would be without the cloud's influence. This displacement is relevant to the Andromeda question because the Milky Way-Andromeda collision calculation depends on knowing the exact position and velocity of both galaxies with precision. The Large Magellanic Cloud changes those numbers. Its gravitational pull introduces a lateral component to the Milky Way's motion, a sideways nudge that in roughly half the simulations run by Sawala's team is enough to redirect the Milky Way away from a direct collision path with Andromeda. So the satellite may, in an ironic and massive way, be the force that keeps our galaxy intact. Or it may not be enough. The uncertainty in the calculation is genuine and significant. Scientists cannot resolve it with current data because the precise mass of the Large Magellanic Cloud is still not perfectly known, and small uncertainties in that mass produce large differences in the long-term trajectory. What is certain is that the Large Magellanic Cloud is currently falling deeper into the Milky Way's gravitational field. Models suggest it will likely be fully absorbed into the Milky Way over the next several billion years. Its stars stripped away and merged into the Milky Way's outer halo. Its dark matter dissolved into the larger halo. The satellite that may have altered the trajectory of the entire Milky Way-Andromeda collision is itself being consumed by the galaxy it is trying to redirect. And while that slow absorption continues, the Large Magellanic Cloud's current passage through the Milky Way's outer disk is already leaving marks: disrupted stellar orbits, perturbed gas clouds, and gravitational disturbances in the regions it has passed through. These marks are being found. They look in many ways similar to the disturbances attributed to dark matter subhalos. The galaxy is being shaped, right now, by a satellite most people have never heard of, and the satellite is only one of several forces currently acting on the structure of the Milky Way from the outside. There may be far more of those forces than anyone previously suspected. The Milky Way may be surrounded by up to 100 galaxies we have never seen. New supercomputer simulations published in July 2029 suggest that the Milky Way could have dozens of faint, undetected satellite galaxies, so-called ghost galaxies, orbiting at various distances through its outer halo. Current observations account for roughly 60 known satellite galaxies, including the Large Magellanic Cloud, the Small Magellanic Cloud, and a collection of ultra-faint dwarf galaxies detected over the past 2 decades. The simulations suggest that number may be only a fraction of the total. These ghost galaxies are not invisible because they emit no light. They are invisible because they emit so little light that they fall below the detection threshold of every telescope pointed at the sky. They are dominated by dark matter. Their stellar populations are sparse. Sometimes only a few thousand stars spread across hundreds of light years. The ratio of dark matter to visible matter in these systems is extreme. Some ultra-faint dwarfs have dark matter fractions exceeding 99% of their total mass. They are, in practical terms, dark matter halos that happen to collect just enough stars to technically qualify as galaxies. What this means for the Milky Way is significant. Each of these satellite galaxies carries its own clump of dark matter. As they orbit the Milky Way, they pass through the outer disk, through the stellar halo, through the regions where stellar streams like GD1 travel. Their gravitational presence creates disturbances. At close enough range, they can perturb stellar orbits, scatter stream stars, and carve features into the fabric of the galactic disk. The disruption attributed to a dark matter subhalo in the GD1 stream may, in at least some cases, actually be caused by one of these undetected satellite galaxies passing through at the right time and place. The line between a dark matter subhalo and an ultra-faint dwarf galaxy is in practice extremely thin. A subhalo that accumulated enough gas and formed a handful of stars becomes a dwarf galaxy. One that formed no stars at all remains a dark matter subhalo, invisible, detectable only through its gravitational effects on things we can see. The Milky Way's outer regions are expected to be filled with both, distributed through the halo in a pattern shaped by billions of years of orbital evolution and close encounters. Finding these systems directly requires pushing the sensitivity of telescopes to their current limits. The European Space Agency's Gaia mission, which mapped billions of stars across the Milky Way from 2014 to 2025, has already revealed several previously unknown dwarf galaxy candidates by identifying coherent groups of stars moving together through the outer halo. The Vera C. Rubin Observatory, with its unprecedented depth and sky coverage, is expected to find more. Scientists have made specific predictions about where additional faint satellites should appear, based on the simulations, and those predictions are now being tested against Rubin's early data. What these ghost galaxies represent is a population of moving objects within the Milky Way that has been acting on the galaxy's visible structure for billions of years, without being seen. They are not static. They orbit, they pass through, they disturb. And because they are almost entirely made of dark matter, their effects look nearly identical to the effects of pure dark matter subhalos. Distinguishing between them requires either direct detection of the faint stellar population, which demands extremely deep imaging, or very precise modeling of the gravitational disturbance signature, which requires much more complete maps of stellar stream shapes across the full sky. Both of those things are now being built, and as they come online, the inventory of what is actually orbiting the Milky Way is about to grow substantially. Some of what we have been calling invisible dark matter structures may turn out to have stars, very faint ones hidden inside them. Others may be purely dark. Either way, the galaxy is surrounded by far more orbiting objects than the current star charts show, and several of those objects may already be passing through regions close enough to affect us. Not all of the disturbances in the Milky Way come from the outside. Within the disk of the galaxy, the flat rotating plane where our solar system sits, there are stars whose motions do not match what the visible mass of the galaxy predicts. The standard way to measure galactic mass is straightforward in principle. Measure how fast stars and gas clouds orbit the center at different distances, and work backward to determine how much mass is pulling on them. If the galaxy's mass were concentrated in its visible disk of stars and gas, orbital speeds should drop off with distance, the way planets in the outer solar system orbit more slowly than those near the center. They do not. Orbital speeds in the Milky Way remain roughly flat or even slightly increase at large distances from the center. Stars at the outer edge of the visible disk orbit just as fast as stars much closer in. By every gravitational calculation, that should be impossible if the only mass present is the visible stars and gas. The explanation that has been accepted for decades is that a large halo of invisible dark matter surrounds the entire galaxy, providing additional gravitational pull that keeps outer stars moving at the speeds they are observed to travel. This is the core of the dark matter hypothesis applied to galaxies, and it works. The numbers match when you add the right amount of dark matter in the right distribution, but the exact shape of that distribution, where the dark matter is densest, how it is concentrated at the center versus spread through the outer halo, how it has been disturbed by the galaxy's history of mergers and interactions, is still being worked out. What has become increasingly clear from observations is that the distribution is not smooth. The gravitational wake left by the Large Magellanic Cloud, the distorted inner halo revealed by Johns Hopkins simulations, the dense subhalos implied by stellar stream gaps, and the overall embedding of the local group in a larger dark matter sheet. All of these point to a dark matter structure that is lumpy, asymmetrical, and actively being reshaped by the galaxy's ongoing dynamics. That reshaping has observable consequences for stars in the disk. As dark matter clumps pass through the disk at different angles and speeds, they gravitationally excite the stars they encounter, nudging them slightly out of their expected orbital planes. creating ripples in the disk's structure. These ripples have been observed. The Gaia mission's star maps revealed vertical oscillations in the Milky Way's disk, waves moving up and down through the galactic plane that cannot be fully explained by the visible mass of the disk alone. Some of these oscillations match the expected signal of a satellite galaxy, or massive clump having passed through the disk in the relatively recent past. The disk of the Milky Way is not the flat, serene structure it appears to be in artist illustrations. It is rippling. It is being perturbed from above and below by passing masses. Its dark matter environment is asymmetrical and dynamic, and somewhere in the outer halo, multiple sources of gravitational disturbance are currently in motion. Some of them ghost galaxies, some of them pure dark matter structures, and possibly some of them things that do not yet have a confident classification. The disk's response to all of this is encoded in the positions and velocities of billions of stars. Gaia spent over a decade measuring those positions and velocities. The data is now being analyzed. The patterns emerging from it are pointing toward a Milky Way that is far more actively disturbed than any model from 20 years ago predicted. And that active disturbance is not just a historical record. Some of it is happening right now. NASA's Fermi Gamma Ray Space Telescope, launched in 2008, within its first few years of operation, it began detecting something at the center of the Milky Way that the mission's scientists could not immediately explain. A diffuse glow of high-energy gamma rays was coming from the galactic center, more gamma ray emission than known astrophysical sources could account for. Researchers called it the galactic center excess, and it has been one of the most actively debated signals in astrophysics ever since. Gamma rays are produced by the most energetic processes in the universe. Supernovae produce them, neutron stars produce them, rapidly spinning dead stars called millisecond pulsars produce them. Cosmic ray particles colliding with gas produce them. All of these processes happen at the galactic center, where stellar density and star formation activity have been high throughout the Milky Way's history. The question is whether the total gamma ray output from all of those known sources adds up to what Fermi is measuring. It does not, quite. There is an excess, an amount of gamma ray emission above what every known source combined can explain. One leading explanation is a large, unresolved population of millisecond pulsars. These objects are numerous, and individually they emit too faintly to be detected by current instruments at galactic center distances. If thousands of them are clustered there, their combined emission could produce something resembling the observed excess. The problem is that the shape of the excess, how it spreads across the sky from the galactic center, does not match perfectly with what a population of pulsars should produce. Pulsars would cluster along the galactic disk and bulge in a specific way. The observed excess is more spherical and smoother than the pulsar model comfortably predicts. The dark matter hypothesis offers a different explanation. If dark matter particles are dense enough at the galactic center and are capable of annihilating each other when they collide, releasing energy as gamma rays, the resulting signal would be spread spherically around the center, following the dark matter density profile, rather than the stellar distribution. The shape of that predicted signal matches the excess better than the pulsar model does. The Johns Hopkins team's 2025 analysis tightened this match by incorporating the realistic, non-spherical dark matter distribution produced by the Milky Way's actual merger history. When that distorted dark matter shape was used instead of a smooth theoretical halo, the gamma ray prediction matched the observed excess more closely than any previous model. The result is not a confirmation. It is a narrowing of the gap between theory and observation. But it is the most precise narrowing yet, and it uses the most realistic treatment of the galactic center's dark matter structure ever applied to the problem. The debate between pulsars and dark matter as the source of the galactic center excess is not resolved, but the dark matter side of that debate is now supported by more evidence than it was even 2 years ago. What makes this significant beyond the immediate puzzle is what it implies about detectability. If dark matter particles annihilate at the galactic center and produce gamma rays, it means they interact, not with light, not with ordinary matter in any strong way, but with each other. That self-interaction would make dark matter something more complex than the featureless ghost-like substance it is often described as. It would mean dark matter has internal physics, properties, a behavior that produces measurable consequences. And if that is true, those consequences should appear in more places than just the gamma-ray glow at the center of the Milky Way. The standard picture of dark matter is deliberately simple. Dark matter does not emit light. It does not interact with light. It does not interact with ordinary matter through any force except gravity. It clumps under gravity, it forms halos, and otherwise it passes through everything, walls, planets, stars, as if they were not there. This simplicity is mathematically useful. It produces galaxy rotation curves that match observations. It explains the large-scale structure of the universe reasonably well. But several observations at smaller scales do not fit the simple picture cleanly. The gaps in stellar streams require subhalos denser than simple cold dark matter predicts. The galactic center excess prefers a dark matter distribution shaped by more complex dynamics than the basic model allows. And the cores of small satellite galaxies, dwarf galaxies that orbit the Milky Way and similar galaxies, tend to have flatter central mass distributions than the simple model predicts. Simple cold dark matter models predict a sharp spike in density at galaxy centers, a cusp. Observations tend to show a smoother central region, a core. This discrepancy has been called the core cusp problem, and it has driven theoretical physicists to explore alternatives. Self-interacting dark matter is one of the most developed alternatives. In this model, dark matter particles occasionally collide with each other, not producing light or gamma rays necessarily, but exchanging momentum the way particles in a gas collide. This self-interaction does not change the large-scale behavior of dark matter much. Halos still form, galaxies still rotate at the observed speeds, the cosmic web of structure still assembles correctly. But at smaller scales, the self-interaction smooths out the central density spike into a core. It allows dark matter to redistribute itself in response to gravitational and energetic processes in ways that simple cold dark matter cannot. And it produces subhalos with density profiles that could, under the right conditions, be compact enough to carve gaps in stellar streams like GD1. The proposal from the University of California Riverside team, published in 2205, connected these ideas directly. Their analysis showed that the gap in the GD1 stream requires a perturbing mass with a density higher than standard cold dark matter subhalos are expected to achieve. A self-interacting dark matter subhalo, however, could reach that density because the self-interaction allows the central region to concentrate mass more efficiently. The gap, in their model, is a direct fingerprint of dark matter that behaves in a physically richer way than the simplest version of the theory. If this interpretation is correct, it means the Milky Way's stellar streams are not just records of gravitational history, they are laboratories. Each stream gap, each kinked trajectory, each unexplained width or misalignment is potentially a measurement of a dark matter property that cannot be tested in any other way currently available. The galaxy itself is the instrument. The stars scattered across its halo are the data points, and the pattern of disturbances they preserve encodes information about what kind of particle dark matter actually is. This would represent a fundamentally different approach to one of physics's deepest unsolved problems. Decades of dedicated particle physics experiments, underground detectors filled with ultra-pure crystals, vast vats of liquid xenon, detectors in deep mines on multiple continents have searched directly for dark matter particles interacting with ordinary matter and found nothing definitive. The galaxy may be offering a different route, not detecting the particle in a laboratory, but reading its properties from the damage it leaves behind across billions of years of galactic history. The stellar stream evidence is still being gathered and interpreted, but the direction it is pointing, toward dark matter that interacts with itself, connects naturally to the three unexplained signals at the galactic center: the distorted inner halo, the dense subhalos implied by stellar stream gaps, and the broader picture of a Milky Way, whose dark matter structure is more complex than any clean model predicted. The simplest version of dark matter is becoming harder to defend, and the more complex version has a specific implication that scientists are now preparing to test directly. In July 2005, a theoretical prediction arrived that reframed what invisible matter might be doing inside the Milky Way right now. Not in the outer halo, not at the galactic center, but inside individual stars. A team of physicists proposed that a specific class of faint, cold stellar objects, sometimes called dark dwarfs, could exist in regions of the galaxy where dark matter density is high. The mechanism they described works like this. If dark matter particles can annihilate each other when they collide, the energy released in those annihilations can heat the interior of a star. In a normal star, energy comes from nuclear fusion, hydrogen atoms fusing into helium deep in the core, releasing enormous amounts of heat and light. But in an environment where dark matter is dense enough, annihilation events could occur inside a small, faint star to supplement or even replace the energy that fusion would normally provide. These dark dwarfs would be real stars with real mass, but they would be kept alive by a different power source than ordinary stars use. Their surface temperatures would be lower than expected for their mass. Their luminosity would be unusual. Their lifespans could extend far beyond what stellar physics normally allows for objects of their size. This remains a theoretical prediction. No confirmed dark dwarf has been identified. The prediction is based on physically reasonable assumptions about dark matter annihilation cross-sections and dark matter density profiles in galactic regions where stellar streams and globular clusters are found. It is, as of 2025, a hypothesis that specific observational signatures could confirm or rule out. But the hypothesis matters because of what it implies about the galaxy we live in. If dark matter density varies significantly from one region of the Milky Way to another, which all current evidence suggests it does, then stars in high-density regions may genuinely behave differently than stars in low-density regions. The dark matter environment is not just a gravitational backdrop, it is a source of energy that varies across the galaxy. Stars moving through dense subhalos, stars orbiting close to the galactic center, stars in the cores of satellite galaxies with extreme dark matter fractions. All of these could in principle be subtly different from stars in our own neighborhood, powered in part by something we cannot directly see. The search for these objects is beginning. Identifying them requires finding stars with luminosity and temperature combinations that do not fit standard stellar evolution models, and then ruling out every other explanation for the anomaly. The Vera C. Rubin Observatory's Deep Sky Survey, combined with spectroscopic follow-up from other instruments, could potentially flag candidates. The challenge is that faint, cold stars are numerous. Separating a genuine dark matter-powered object from a standard ultra-cool dwarf or a brown dwarf requires careful multi-wavelength analysis. If dark dwarfs are real, they would represent a population of objects distributed through the densest regions of the galactic dark matter halo, a class of stars that the galaxy has been generating across its entire history. Invisible, not because they emit no light, but because they emit so little that they have always been below detection thresholds. Their existence would confirm that dark matter is not merely a structural element of galaxies, it is an energy source, active, ongoing, woven into the life cycle of stars in ways that no model from even a decade ago considered seriously. The Milky Way in that picture is not a galaxy lit only by fusion. It may be a galaxy that glows in places from something else entirely. Step back from each individual finding, and the combined picture becomes striking. An interstellar comet arrived from the galactic center, moving at over 150,000 miles per hour. Chemically unlike anything formed in our solar system, potentially billions of years older than our planet, carrying the fingerprints of a part of the galaxy we have never visited and never will. It is the third such object in 8 years. Calculations suggest thousands of similar objects pass through our solar system undetected every year, moving between star systems across the galaxy in a constant, invisible traffic that connects solar systems that gravity alone could never bridge. Across the Milky Way's outer halo, stellar streams are being disrupted by masses that no known object caused. The gaps in those streams require something denser than standard dark matter models allow, pointing towards self-interacting dark matter, a physically richer substance that clumps and concentrates in ways the simplest models cannot reproduce. New algorithms applied to Gaia's billion-star map have found dozens of hidden streams, many of them wider, shorter, or misaligned in ways that encode the gravitational history of forces that have been moving through the halo for billions of years. At the galactic center, 3 independent signals, positrons, gamma rays, ionized gas, fire consistently in patterns that no known astrophysical process explains simultaneously. A single dark matter mechanism fits all three at once. Supercomputer simulations of the Milky Way's entire merger history suggest that the dark matter at the galaxy's core has been distorted into a lopsided, non-spherical shape by billions of years of collisions. That distorted shape produces a gamma-ray pattern that matches observations more closely than any previous model, and the object we have long assumed sits at the galaxy's center may, some scientists now propose, be a continuous dark matter structure rather than a discrete black hole. Two things that currently cannot be distinguished from the outside. The galaxy itself sits inside a vast flat sheet of dark matter, stretching tens of millions of light years, embedded in a cosmic architecture that controls the motions of every galaxy in our local neighborhood. And the nearest major galaxy, already overlapping with our dark matter halo, is closing in at over 68 miles per second, with a 50% probability of direct collision determined by the gravitational nudge of a satellite galaxy that has only recently been recognized as a significant force in the local universe. Ghost galaxies, up to 100 undetected dwarf systems, may be orbiting the Milky Way right now, each carrying its own dark matter clump, each leaving gravitational marks as they pass through the outer disk. Stars in the highest density dark matter regions of the galaxy may be running on a power source that has never been confirmed. The Milky Way's disk is not flat and serene. It is rippling from the passage of masses through it. None of these findings are disconnected. They are all signatures of the same underlying reality. Dark matter is not a passive, uniform background. It is structured. It is moving. It is being shaped by the galaxy's history and shaping the galaxy's future simultaneously. And the tools we have built, Gaia, Fermi, Vera-C, Rubin, the Very Large Telescope, the Event Horizon Telescope, the Atlas Survey Network, are only now reaching the sensitivity needed to read what that structure is actually doing. The interstellar comet was the most visible signal, but it was a single data point in a much larger pattern. Something has been moving through this galaxy for billions of years. Multiple somethings. Some of them are objects from other star systems. Some of them are clumps of invisible mass, distorting the structure of everything around them. Some of them are entire galaxies closing in from millions of light years away. What we have learned in the past few years is that the Milky Way is not a stable, settled system. It is active, disrupted, and surrounded by forces in motion. And the instruments being built right now will, within the next decade, either confirm what the current evidence is pointing toward, or reveal that the picture is stranger still. The Milky Way does not sit in empty space between galaxies. It sits inside a structure. For half a century, astronomers noticed something strange about the galaxies just beyond our local group. The universe is expanding. Virtually every distant galaxy is moving away from every other one, carried outward by the growth of space itself. The galaxies just outside our local neighborhood should follow that pattern. Most of them do. But the details of their velocities have never fit cleanly. Some move outward slightly too slowly. Some drift in directions that the combined gravity of the Milky Way and Andromeda cannot fully explain. The discrepancy was not enormous, but it was persistent, and it resisted every attempt at a clean solution. The answer, published in Nature Astronomy in early 2200, by a team led by Ewood Wempe of the Kapteyn Institute, came from rebuilding the entire local cosmic environment from scratch. The team started with the faint patterns imprinted on the cosmic microwave background, the earliest detectable signal in the universe. A map of tiny density variations in the hot plasma that filled all of space roughly 400,000 years after the Big Bang. From those patterns, they ran forward-evolving simulations until the model reproduced the present-day masses, positions, and velocities of the Milky Way, Andromeda, and 31 surrounding galaxies simultaneously. What the simulations consistently produced was a large-scale flat structure, a sheet of dark matter extending tens of millions of light-years, oriented in a specific plane. Above and below that plane sit enormous voids, regions nearly empty of galaxies and mass. The local group, the Milky Way, Andromeda, and their satellites is embedded inside this sheet. The gravitational forces pulling along the sheet's plane partially cancel the inward pull of the local group for galaxies sitting within it, keeping them from falling toward us. The galaxies in the voids above and below are simply absent, no mass there to be observed moving in any direction. This sheet is not a wall or a boundary. It is a river of dark matter flowing through the larger cosmic web, the vast network of filaments and voids that forms the large-scale structure of the universe. Galaxies form preferentially along these filaments and sheets, where dark matter is dense enough to anchor them. The Milky Way formed inside one of these concentrations and has remained embedded in it throughout its entire history. The practical consequence is significant. The Milky Way does not experience its cosmic environment uniformly from all directions. It is gravitationally channeled. Mass flows toward it along the sheet's plane. Andromeda moves toward it along that same structure. Even the large-scale direction of the Milky Way's own orbit within the local group is shaped by the sheet's geometry. The galaxy's future, where it ends up, what it interacts with, whether it collides with Andromeda, is being determined not just by the two galaxies themselves, but by the vast dark matter architecture they are both embedded inside. This is the largest scale at which something is moving through our galaxy's environment. Tens of millions of light-years of invisible mass, organized in a plane, channeling the fate of every galaxy within it. The Milky Way is not adrift, it is inside a current. And that current connects directly to the approach of the largest object on a trajectory toward our galaxy. A galaxy that has been measured, modeled, and debated, whose arrival timeline just became substantially less certain. The sheet explains the motions of nearby galaxies. What it cannot tell us is exactly what Andromeda will do when it gets here. The most consequential unresolved question about the Milky Way's future now carries a 50% probability attached to it. Andromeda is real, massive, and approaching. Its dark matter halo already overlaps with the Milky Way's own halo. The two invisible structures surrounding each galaxy have already made contact at their outer edges. The galaxies themselves remain 2.5 million light-years apart. But at 110 kilometers per second of closing speed, that distance is shrinking. The question is not whether Andromeda is coming, the question is whether it will hit. The 2005 study by Tilsawala's team at the University of Helsinki used the most precise available measurements from both Gaia and Hubble to determine Andromeda's exact velocity components, how fast it is moving directly toward us versus how much sideways motion it carries. Both quantities matter enormously for predicting the outcome. A galaxy with a small sideways velocity and a large inward velocity is almost certainly on a collision course. A galaxy with a larger sideways velocity relative to its inward speed may swing past without merging. The updated measurements showed more sideways motion than the 2012 analysis had captured. Not dramatically more, but enough. When combined with the gravitational influence of the Large Magellanic Cloud pulling the Milky Way laterally, to shift the merger probability down to approximately 50%. In about half of the simulations, the galaxies pass each other at a closest approach of roughly 500,000 light-years. In the other half, they collide and begin a multi-billion-year merger process. 500,000 light-years sounds like a safe distance. It is not insignificant. The Milky Way's visible disk spans roughly 100,000 light-years. A galaxy passing at 5 times the disk's diameter would still exert enormous tidal forces, stretching the outer disk, disrupting stellar orbits in the halo, triggering bursts of star formation as gas clouds are compressed. A near miss is not a non-event. It is a gravitationally violent near miss that would permanently alter the structure of both galaxies. In the collision scenarios, the sequence plays out over several billion years. The galaxies first make contact tidally, their disks beginning to distort as they approach. Their first close pass reshapes both structures dramatically. They then pull apart, loop back, and make a second approach. Over successive passes separated by hundreds of millions of years, they gradually merge into a single massive elliptical galaxy, what some scientists have nicknamed Milkomeda. The two central black holes, or whatever massive objects anchor each galaxy's core, would spiral toward each other over millions of years, emitting gravitational waves as they close in, eventually merging into a single object of combined mass. In both scenarios, collision and near miss, the individual stars inside each galaxy are almost certainly safe. Stars are so widely separated inside a galaxy that even a full merger produces essentially no actual stellar collisions. The stars get thrown into new orbits. Our solar system would likely be displaced to a different region of the resulting galaxy. The night sky would look completely different, but the physical survival of planets and stars is not seriously threatened by the merger itself. What changes is everything about the galaxy as a system: its shape, its star formation rate, the distribution of its mass, its relationship to the dark matter halo surrounding it. Everything that defines the Milky Way as a structure gets rewritten. And whether that rewriting begins in 4 billion years or is avoided entirely now depends on the gravitational influence of a satellite that arrived in the Milky Way's neighborhood relatively recently. The collision between the Milky Way and Andromeda, if it happens, is 4 billion years away. The interaction between their dark matter halos is happening right now. Dark matter halos are large. They extend far beyond the visible edges of their galaxies. The Milky Way's halo stretches outward for several 100,000 light-years in every direction, several times the diameter of the visible disk. Andromeda's halo is comparable in size and mass, at a current separation of 2.5 million light-years between the galaxy centers. The outermost edges of these two halos are already in contact. The invisible structures surrounding each galaxy are already overlapping, already exerting gravitational forces on each other, already beginning the slow process that will eventually determine whether the galaxies merge. This overlap is not dramatic in its immediate effects. The outer reaches of a dark matter halo are low-density, diffuse regions where the mass per unit volume is small. The gravitational forces they exert on each other at this stage are subtle, but subtle forces applied over billions of years accumulate. The trajectory of each galaxy through space is being continuously bent by the gravitational pull of the other's halo. Every year that passes with the halos in contact is a year in which the merger probability calculation is being updated by the actual physics of the two systems. What makes this moment scientifically important is that the halo contact is occurring at a time when we have the instruments to detect its effects. Gaia spent over a decade measuring the positions and velocities of stars across the Milky Way's outer regions with extraordinary precision. Some of that data reveals subtle kinematic distortions in the outer halo, regions where stellar motions are slightly more ordered or slightly more disturbed than expected. That may carry the gravitational fingerprint of Andromeda's approach. Separating Andromeda's gravitational influence on the Milky Way's outer halo from the influence of the Large Magellanic Cloud, the ghost satellite galaxies, and the dark matter subhalos moving through the same regions is a complex problem. All of these forces are acting simultaneously. All of them leave overlapping signatures in the data. Disentangling them requires extremely precise modeling of each individual source, building a complete gravitational census of everything affecting the Milky Way's outer structure, and then subtracting each contribution to see what remains. That census is being built right now. The Gaia mission's final data releases are being combined with Vera-C, Rubin Observatory observations, with deep imaging surveys from multiple ground-based telescopes, and with theoretical models refined by the most powerful astrophysical supercomputers currently operating. The goal is a complete map of the Milky Way's mass distribution, visible and invisible, accurate enough to detect the gravitational effects of the approaching galaxy. When that map is complete, it will do more than resolve the Milky Way Andromeda question. It will produce the most detailed picture ever assembled of what dark matter is actually doing inside and around a galaxy in real time, not inferred from rotation curves or cluster dynamics at cosmological distances, but measured directly from the positions and motions of billions of individual stars spread across our own galaxy's structure. Every star in Gaia's catalog is a data point in that measurement. Every stream, every halo star, every outer disk disturbance is a piece of the same picture. The halos are touching. The measurement of that contact is underway, and the implications of what that measurement reveals will extend well beyond the question of whether the galaxies collide. Something has been moving through the disk of the Milky Way, and the disk is still responding. The Milky Way's disk, the flat, rotating plane of stars and gas where our solar system sits, roughly 100,000 light-years across, and a few thousand light-years thick, is not perfectly flat. Gaia's detailed star maps revealed vertical waves moving through it, oscillations where stars above and below the disk's midplane are bobbing up and down in coordinated patterns, like ripples moving across the surface of a pond after something heavy passed through. These waves were first clearly identified in Gaia's early data releases and have been studied in increasing detail since. They are real, measured structures, not noise, not artifacts of the observing technique. The patterns are coherent enough that scientists can estimate roughly when and where the disturbance that caused them originated. The current best analysis points to a relatively recent passage of a massive object through or very close to the disk within the last few 100 million to perhaps 1 billion years. Several candidates have been proposed. The Large Magellanic Cloud is the most prominent. Its approach and current orbit bring it close enough to the outer disk to excite vertical oscillations of roughly the observed amplitude. A passage by a massive dark matter subhalo through the disk plane is another possibility. In principle, an undetected dwarf galaxy could have passed through the disk without leaving a visible stellar trail, its dark matter doing all the gravitational work, and its stars, if it had any, too sparse to be easily identified in the background. What the ripples confirm is that the disk is a dynamic structure being actively perturbed. It is not in a settled equilibrium state. Something with significant mass interacted with it in the astronomically recent past, and the disk is still oscillating from that interaction, the way a bell continues ringing after being struck. The oscillations will eventually damp out as stars' random motions smooth the wave patterns over millions of years. But right now, the wave is still there. The fact that the disk is rippling has a practical implication for how we understand the Milky Way's current state. A galaxy with a smooth, unperturbed disk sits in a relatively quiet, dynamical environment. A galaxy with an actively rippling disk is a galaxy that has been recently disturbed, one whose nearby environment contains massive objects in motion. The ripples are not alarming in any threatening sense, but they are a physical record that the Milky Way has not been sitting undisturbed. Something moved through it. The disk registered the passage. Finding the specific cause of the observed waves requires matching the wave pattern, its amplitude, its spatial frequency, its propagation direction, to the expected gravitational signature of specific candidate objects at specific times. The Large Magellanic Cloud's gravitational influence can be modeled precisely enough to test whether its trajectory matches the wave properties. Dark matter subhalos present a harder problem because their properties and exact orbits are not known in advance. But the wave itself constrains what caused it. The mass and speed of the perturber must fall within a range that produces the observed amplitude. That range rules out very small objects and provides an upper limit on how massive the perturber could be without having been directly detected. The disk is telling scientists something moved through it. The disk's oscillation pattern carries information about what that something was. And decoding that information is now one of the active frontiers of Milky Way science, a problem being attacked simultaneously with stellar kinematic data, gravitational modeling, and satellite galaxy orbit simulations. The answer will tell us something specific about what has been moving through this galaxy recently. And recently, in galactic terms, is close enough to now to matter. Every interstellar object that passes through our solar system carries a record of the galaxy it traveled through. The surface of 3I/Atlas has been exposed to cosmic radiation for somewhere between 3 and 14 billion years. The range scientists currently estimate for its age based on where it came from and what kind of stellar environment its trajectory implies. During that time, every energetic particle streaming through the galaxy, protons accelerated by supernova shockwaves, gamma rays from explosive events, ultraviolet light from hot young stars, has bombarded its surface continuously. The organic compounds in its outer layers have been chemically altered by that radiation, producing the reddish, tholin-rich coating that spectroscopic observations detected during its passage. That coating is not just a curiosity, it is a dosimeter, a record of the total radiation environment the comet experienced across its entire journey. The thickness and composition of the tholin layer encodes information about how much radiation the object received, and at what energies. Comparing the properties of interstellar comet surfaces to those of objects in our own outer solar system, where similar radiation processing occurs, but over shorter timescales in a lower radiation environment, gives scientists a way to estimate how long an interstellar object has been traveling and through what kinds of regions. The galactic center region, where 3I/Atlas is believed to have originated, is one of the highest radiation environments in the galaxy. The density of stars, the frequency of supernovae, the energetic processes near the central mass, all of these produce radiation fields substantially more intense than what prevails in our quiet suburban region of the Milky Way. An object that formed in that environment and spent billions of years traveling outward through the disk would accumulate a distinctive surface chemistry, one that carries the fingerprint of its origin in a way that laboratory analysis can, in principle, partially decode. The cyanide gas detected in the comet's coma adds another layer. Cyanide is a relatively simple molecule, a carbon atom bonded to a nitrogen atom, but it is also one of the molecular building blocks that prebiotic chemistry relies on. Some of the earliest plausible chemical pathways toward life-relevant molecules involve cyanide as a starting material. Detecting it in the coma of an object that has traveled for billions of years through the galaxy raises a question that scientists are genuinely debating. Do interstellar objects like this one carry organic chemistry between star systems? The honest answer is that no one knows yet. What is established is that 3I/Atlas contains organic compounds on its surface and cyanide gas in its outgassing coma. Whether those compounds are complex enough to be genuinely prebiotic, capable of contributing to chemistry relevant to life, if they landed in the right environment, requires analysis of a kind that remote spectroscopic observation from Earth cannot currently provide. A sample return mission, or even a close flyby with a highly instrumented spacecraft, would be necessary to answer the question properly. But the question itself, whether the galaxy's interstellar objects are moving chemistry between star systems, is now scientifically serious in a way it was not before 3 confirmed interstellar visitors demonstrated that such objects actually reach inner solar systems. The mechanism exists. Objects travel between stars. They carry surface chemistry shaped by their origin environments. Whether that chemistry matters biologically is the next question, and answering it requires catching one of these objects close enough and early enough to study it properly. That problem has driven a specific engineering and scientific effort that is now actively underway. When 3I/Atlas was detected on July 1st, 2025, the discovery set off a global scramble. Telescopes on every continent pivoted toward it. Archival data from multiple survey systems was pulled and searched for pre-discovery observations stretching back to mid-June. The Very Large Telescope in Chile, the Gemini Observatory, the International Gemini Facility, the Vera C, Rubin Observatory, and eventually ESA's ExoMars Trace Gas Orbiter and NASA's Mars Reconnaissance Orbiter all contributed observations. Scientists had months, not years, before the object passed its closest point to our star and began its outbound journey. By September, it had moved too close to the sun's glare for ground-based observation. By December, it was making its final close approach to Earth before departing the solar system permanently. The scientific return from those months of observation was substantial, but researchers agree it was far less than what a dedicated mission to the object's vicinity could have produced. Remote spectroscopy can identify the chemical species in a coma and make inferences about surface chemistry. A spacecraft equipped with mass spectrometers, cameras, and dust analyzers orbiting or flying alongside the object could measure its composition directly, characterize its nucleus size and shape, sample its outgassing in detail, and potentially even land or retrieve material. None of that was possible in 2005 because no spacecraft was ready. The engineering community has been aware of this gap since Oumuamua. After that discovery, multiple mission concepts were proposed. Project Lyra, developed by the Institute for Interstellar Studies, analyzed the feasibility of chasing Oumuamua, which was already on its outbound trajectory by the time it was confirmed interstellar. The conclusion was that catching it required propulsion systems faster than anything currently operational. Options included solar sails, large lightweight structures that use radiation pressure from our star as propulsion, and nuclear-powered spacecraft with higher thrust-to-mass ratios than conventional chemical rockets. The critical challenge is response time. An interstellar object moving at over 150,000 miles per hour traverses the inner solar system in a matter of months. A mission that requires years of planning and development after discovery will always be too slow. The solution being developed is a standing readiness capability, a spacecraft kept in a state of near-launch readiness, designed to be deployed within weeks of a confirmed interstellar object discovery. Some proposals involve positioning such spacecraft at gravitationally favorable points in the solar system, where the launch window to intercept incoming objects is maximized. Artificial intelligence systems are being incorporated into the detection and response pipeline. Current survey telescopes generate enormous data volumes. The Vera-C Rubin Observatory alone will capture roughly 15 terabytes of image data per night. Identifying an interstellar object in that data stream quickly enough to allow meaningful mission planning requires automated algorithms capable of recognizing the signature of a hyperbolic trajectory and flagging it for human follow-up, faster than any manual process could manage. The scientific community is building toward a future where the next interstellar visitor is not merely observed from a distance for a few months, but actually intercepted. The knowledge gap between remote observation and in situ measurement is enormous. Closing that gap requires infrastructure, fast spacecraft, ready missions, smart detection systems that does not yet exist in its complete form. Building it is now a stated priority for multiple space agencies. The next interstellar object is coming. Scientists intend to be ready. One of the oldest questions in biology is where life on Earth came from. The chemical complexity required for even the simplest living cell is extraordinary. The probability of that complexity assembling spontaneously in a single location, purely by chance, has always been a source of scientific debate. One proposed partial answer, not widely accepted but also not dismissed, is that the organic chemistry relevant to life is more widespread in the universe than Earth-centric thinking assumed, and that some of it arrives here from space. This idea, broadly called panspermia, takes different forms with different degrees of scientific support. The weakest version, that complex life, or living organisms, travel between star systems, has essentially no credible evidence behind it, and most scientists do not take it seriously as a mechanism. A more defensible version is simpler, that organic molecules, the chemical precursors to biological molecules, are present in space and are delivered to planets by comets and asteroids. This version is well supported. Amino acids, the building blocks of proteins, have been found in meteorites. Complex organic molecules are detected in interstellar gas clouds by radio telescopes. The basic chemistry of life is not uniquely terrestrial. What the confirmed detection of 3 interstellar objects in 8 years adds to this picture is a specific delivery mechanism operating at galactic scales. If interstellar comets carry organic chemistry on their surfaces, cyanide, tholins, more complex compounds that closer analysis might reveal, and if these objects genuinely pass through inner solar systems in significant numbers every year, then organic material from distant star systems is regularly entering environments where planets with liquid water exist. Whether that material survives atmospheric entry in a form that could contribute to prebiotic chemistry is a separate and genuinely unresolved question. Whether the chemistry of 3I/Atlas specifically is complex enough to be biologically relevant is unknown. The observations made during its passage were not detailed enough to answer it. But the framework for galactic-scale chemical transport now has observational grounding. The objects exist. They move between systems. They carry surface chemistry shaped by their origin environments and their long journeys through the galaxy. The galactic center, where 3I/Atlas likely originated, is one of the densest repositories of molecular complexity in the Milky Way. The central molecular zone contains enormous clouds of gas and dust rich in organic molecules. Stars forming inside those clouds produce comets incorporating that molecular material. Some of those comets get gravitationally ejected into interstellar space. A fraction of those ejected comets, over billions of years, find their way to other star systems. One of them, apparently, found its way to ours. The idea that the Milky Way may be moving chemistry between its star systems, not directed by any mechanism other than gravity and orbital dynamics, is now supported by enough evidence to be taken seriously as a hypothesis worth testing. Testing it requires more interstellar objects, studied more closely. It requires the interceptor missions being planned. And it requires understanding the broader context of what is moving through the galaxy, because the interstellar objects are only the most visible thread in a much larger pattern. The pattern involves not just what moves between stars, but what moves through the galaxy itself, at every scale. And one of the most important things moving through the Milky Way is something that cannot be seen at all. The solar system is not stationary inside the Milky Way. It orbits the galactic center at roughly 500,000 miles per hour, completing one orbit every 225 million years. The Milky Way's dark matter halo does not rotate the same way. While the visible disk rotates in a relatively ordered pattern, the dark matter halo is thought to be in a different dynamical state, more dispersed in its motions, with dark matter particles following their own orbital paths throughout the halo in directions that do not all align with the disk's rotation. The consequence is a dark matter wind. From the perspective of the solar system moving through the halo, dark matter particles arrive preferentially from one direction, the direction the solar system is moving toward. This is the same effect that makes rain appear to fall toward a moving car's windshield, even when it is actually falling straight down. As the solar system orbits through the halo, it encounters dark matter streaming from a particular direction at a particular average speed relative to us. The expected speed of dark matter particles in the solar system's neighborhood, based on the known dynamics of the halo, falls in a range that particle physicists have used for decades to design their underground detectors. Those detectors, filled with ultra-pure xenon, germanium, or other materials, are built to be sensitive to the kind of energy deposited by a dark matter particle hitting an atomic nucleus at the expected relative speed. The dark matter wind sets the target. The detectors try to measure it directly. So far, no detector has produced a confirmed, reproducible detection of a dark matter particle. This is not a minor experimental inconvenience. Decades of progressively more sensitive experiments, reaching detection thresholds that were once considered impossibly demanding, have returned no clear signal. The detectors are sensitive enough that they should be seeing something. If dark matter particles interact with ordinary matter through any mechanism beyond gravity, at the rate some theoretical models predicted, the silence of the detectors is itself information. It has ruled out large regions of the theoretical parameter space. What it has not done is rule out dark matter entirely. Several viable theoretical candidates remain consistent with the detector null results. Lighter particles, more weakly interacting particles, and particles that interact through mechanisms other than the ones current detectors are designed to measure, are all still plausible. Self-interacting dark matter, the candidate suggested by the stellar stream gaps, interacts with itself, but may interact with ordinary matter even more weakly than standard models assumed, placing it below current detector thresholds. The dark matter wind is real in a statistical sense. The solar system is moving through a halo of something that exerts gravitational influence on every orbit in the galaxy. What that something is made of, at the particle physics level, remains unknown after decades of searching. The galactic scale observations, stream gaps, gamma-ray excesses, disturbed disk waves, ghost galaxy distributions, are now generating a set of constraints on dark matter's properties that the underground detectors alone could not provide. The two approaches are converging on the same problem from different directions. One is trying to catch a dark matter particle in a laboratory. The other is reading the gravitational damage dark matter has done to an entire galaxy over billions of years. Both approaches are producing results. The question is which one will produce the definitive answer first. The gap between what scientists currently know and what they need to know is being closed by a specific set of instruments. Some already operating, some recently completed, some under construction, each designed to push one part of the dark matter and galactic structure problem past a current limit. The Vera C. Rubin Observatory in Chile began its legacy survey of space and time in 2005. Over 10 years, it will photograph the entire accessible southern sky. Every few nights, with a camera so large and sensitive that it will detect objects roughly 100 times fainter than any previous comparable survey. For the Milky Way, this means finding stellar streams too faint to appear in earlier data, identifying ultra-faint satellite galaxies below previous detection thresholds, and catching interstellar objects earlier in their solar system passage, giving more time for observation and, eventually, for mission responses. The European Space Agency's Gaia mission completed its primary science operations in 2005, after more than a decade of continuous sky monitoring. The final full data release, containing the most precise positions, proper motions, and parallaxes for billions of stars ever assembled, is being processed and will represent the most detailed kinematic map of the Milky Way ever produced. This map is the primary tool for reading the gravitational history encoded in stellar stream shapes, disk oscillations, and outer halo disturbances. Analyzing it fully will take years, and each analysis will extract more information about what dark matter has been doing to the galaxy's structure. The square-kilometer array, currently under construction across South Africa and Australia, will be the most powerful radio telescope ever built, a system of thousands of individual antennas spread across 2 continents, combined into a single effective collecting area of 1 square kilometer. Among its many scientific targets is the ability to detect pulsars at the galactic center, with sensitivity far beyond current instruments. If the galactic center excess is caused by a large population of millisecond pulsars, the square kilometer array should be able to detect enough of them individually to resolve the question. If the excess remains after those detections and still cannot be explained by the pulsar population found, the dark matter explanation gains substantially stronger support. The James Webb Space Telescope, now in its 4th year of operations, is contributing to the interstellar object problem through deep infrared observations of incoming comets and asteroids, giving scientists access to wavelengths where thermal emission from cold, dark surfaces is detectable. It was proposed for observations of 3I/Atlas, and its infrared sensitivity opens the possibility of characterizing the surface chemistry of future interstellar visitors in more detail than visible light instruments allow. Gravitational wave detectors, the Laser Interferometer Gravitational Wave Observatory in the United States, and its partner Virgo in Europe, are being upgraded to higher sensitivity. If 2 supermassive black holes, or 2 massive dark matter cores, eventually merge at the center of a future galaxy collision, they would produce gravitational waves detectable across cosmic distances. The merger of the Milky Way and Andromeda's central objects, whatever those objects ultimately prove to be, would be one of the most powerful gravitational wave events in the local universe. These instruments are not studying separate problems. They are all pointing at the same underlying question: what is the Milky Way made of? What is moving through it? And what is coming toward it? The answers are converging from multiple directions simultaneously, and the picture they are assembling is more dynamic, more structured, and more interconnected than any model from a generation ago predicted. The Milky Way may be surrounded by roughly 100 satellite galaxies that have never been catalogued. Current observations confirm approximately 60 known satellites, systems ranging from the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere, down to collections of a few thousand stars spread across hundreds of light years, detected only through their statistical excess above the background galaxy count in deep imaging surveys. Each of these known satellites contributes to the gravitational environment of the Milky Way. Each carries dark matter. Each perturbs the outer halo as it orbits. The simulations published in 2025 suggest the real number may be roughly double what current observations have found. The missing systems are not absent from the universe. They are present, but below current detection thresholds. Their stellar populations are so sparse that even deep surveys struggle to distinguish them from statistical noise in the background galaxy population. The predicted properties of these missing satellites, their sizes, their dark matter fractions, their orbital distribution, are constrained by the same cosmological models that predict their existence. They should be there. Finding them requires instruments sensitive enough to detect objects at the ragged edge of what qualifies as a galaxy. The Vera C. Rubin Observatory is expected to find a significant fraction of this hidden satellite population within its first few years of operation. Predictions made before its first data release specified both the number and approximate sky locations where new satellites are most likely to appear based on the expected orbital distribution. Matching those predictions against actual discoveries will be a critical test of the models and of the dark matter distribution that drives them. Each newly confirmed satellite is simultaneously a data point for the dark matter model and a new gravitational influence to account for in the Milky Way's dynamical census. One satellite, whose orbital history brings it close to the galactic disk, can leave wave signatures similar to those Gaia detected. One satellite passing through a stellar stream region can produce gaps that look identical to dark matter subhalo disturbances. Knowing which satellites exist, where they orbit, and what their masses are, is a prerequisite for correctly interpreting every other anomaly in the Milky Way structure. There is also a cosmological implication. The number of satellite galaxies orbiting the Milky Way is a prediction of the lambda-cold dark matter model, the standard cosmological framework. Early versions of that model predicted far more satellites than observations had found, a discrepancy that was a significant problem for the theory for years. More recent versions of the model, incorporating the effects of stellar feedback, the way stars' radiation and explosions heat and expel the gas needed for star formation, predict far fewer satellites that are luminous enough to detect, bringing the prediction closer to the observed number. If Rubin finds 100 additional satellites rather than the 20 or 30 that had been expected to be hiding, it would be a significant input into how the model is calibrated. The ghost population is being mapped. Its discovery will simultaneously solve several outstanding puzzles and create new ones. Every satellite found is a satellite whose gravitational history must be accounted for. Every satellite not found where the model predicts it should be is a constraint on the physics of dark matter and galaxy formation. The inventory of what orbits the Milky Way is one of the most active frontiers in galactic astronomy, and it is about to expand substantially. The detection of cyanide in 3I/Atlas's coma was one data point in a much larger picture that has been building for decades. Radio telescopes have been detecting complex organic molecules in interstellar gas clouds, the dense, cold regions of the galaxy where stars form, for over 50 years. The list of molecules detected in these clouds now extends to well over 200 distinct chemical species, including amino acid precursors, simple sugars, alcohols, and molecules with carbon chain structures that shade into the lower ranges of organic chemistry. These detections come from clouds across the Milky Way, from the dense molecular regions near the galactic center to star-forming regions in the spiral arms thousands of light-years from the center. The Atacama Large Millimeter Array in Chile, a system of 66 high-precision radio antennas, has been the primary instrument for characterizing the molecular content of star-forming regions in detail. Its sensitivity allows it to detect molecules in clouds where new stars are currently forming, meaning the organic chemistry present in those clouds will be incorporated into the comets, asteroids, and eventually planets that form in those young stellar systems. The organic inventory of those forming systems is not assembled locally from scratch. It is inherited from the molecular cloud that gravity collapsed to form the stars. What this means at galactic scale is that the Milky Way is, in a real sense, a chemically connected system. The organic molecules in molecular clouds near the galactic center are related to those in clouds in the spiral arms. The comets that form in young stellar systems incorporate chemistry from those clouds. Some fraction of those comets are eventually ejected into interstellar space. A fraction of the ejected ones travel to other star systems, and the chemical record they carry is ultimately derived from the large-scale molecular environment of the galaxy itself. The interstellar objects are the visible tip of this chemical connectivity. The question of whether they deliver anything biologically significant to the planets they pass, whether the organic chemistry they carry survives the delivery process and contributes meaningfully to the chemistry of those worlds, cannot be answered from current observations. But the connectivity itself is now demonstrated. The galaxy moves chemistry. The mechanism is gravitational ejection and interstellar transit. The frequency is high enough that inner solar systems receive these visitors regularly. Whether any of that chemistry has contributed to life anywhere in the galaxy, including here, remains one of the deepest open questions in science. What the past decade of observations has established is that the question is not absurd. The molecules are real, the transport mechanism is real, the frequency of interstellar objects is real. Everything in the chain, from molecular cloud to comet to interstellar transit to solar system delivery, has observational grounding. The biological endpoint is the one piece that has no confirmed example beyond Earth. And that example, life on Earth, is the only data point we currently have for whether any of this chemistry ever crosses the gap between space and biology. Whether it crossed that gap here, or whether Earth assembled its own chemistry independently, cannot yet be determined. But the question now sits firmly inside the boundaries of testable science, rather than speculation. The Milky Way was not assembled quietly. The galaxy we inhabit today is the product of billions of years of collisions. Smaller galaxies swallowed whole, streams of stars stripped from infalling systems and absorbed into the halo. Waves of star formation triggered by each major merger event. This violent history is not a distant story. Its evidence is embedded in the structure of the galaxy right now, readable in the kinematics of halo stars, the composition of stellar populations at different distances from the center, and the shape of the dark matter distribution that was distorted by every major collision. Gaia's precision measurements of stellar positions and motions allowed astronomers to identify several major merger events in the Milky Way's past. The largest of these, a collision with a galaxy sometimes called Gaia Enceladus, or the Sausage Galaxy, that occurred roughly 8 to 10 billion years ago, contributed a substantial fraction of the inner halo's stellar population. The stars from that absorbed galaxy still orbit the Milky Way today, identifiable by their chemical compositions and orbital properties despite being billions of years old. They did not come from here. They were absorbed. Several other significant merger events have been identified in the stellar record. Each one deposited stars and dark matter into the Milky Way. Each one disrupted the existing dark matter distribution, reshaping the halo from whatever geometry it had before the merger into something different. The Johns Hopkins team's use of realistic merger histories in their simulations of the galactic center's dark matter structure, rather than assuming the halo had always been spherical and smooth, was motivated precisely by this evidence. The halo's current shape is the cumulative result of every major collision the galaxy has experienced. This merger history is still ongoing. The Large Magellanic Cloud is in the process of being absorbed. The Sagittarius Dwarf Galaxy, a satellite currently being torn apart by the Milky Way's tidal forces, is depositing its stars into the halo in long streams that wrap around the galaxy multiple times. Several smaller satellites are following similar trajectories. The Milky Way is still growing by accretion, still absorbing nearby systems, still adding their stars and dark matter to its own structure. The Andromeda Galaxy has a comparable merger history. Its stellar halo contains the remains of absorbed satellites visible as streams of stars, stretching across hundreds of thousands of light years. When the two galaxies' halos interact, as they are already doing at their outer edges, the dynamical histories of both systems become entangled. The dark matter from Andromeda's mergers and the dark matter from the Milky Way's mergers are already beginning to feel each other's gravity. The long process of their interaction, however it ultimately resolves, is the next chapter in the merger history of both galaxies. What this history reveals is that the Milky Way as it exists today is not a pristine object. It is a composite, built from pieces of other galaxies, shaped by collisions, carrying the chemical and dynamical signatures of systems that no longer exist independently. The stars overhead tonight include the remains of galaxies that were destroyed. The dark matter surrounding us includes the halos of absorbed satellites. The structure of the galaxy at every scale has been shaped by things that moved through it. That process of shaping has not stopped. Beyond the visible disk, beyond the region where most of the Milky Way stars orbit, the outer halo extends into a vast and sparsely populated region that stretches several 100,000 light-years in every direction. This region is not empty. It contains the faint outer stars of the galaxy, moving in orbits that take them far from the center and back again over billions of years. It contains the known satellite galaxies and the predicted ghost satellites. It contains stellar streams, thin trails of stars shed from clusters and absorbed dwarf galaxies, preserving the orbital history of the forces that shaped them. And it contains the dark matter subhalos, the invisible clumps moving through the halo on their own orbital paths, periodically passing close enough to stellar streams or the disk itself to leave detectable marks. The outer halo is the most sensitive region of the galaxy for detecting disturbances. Stars there orbit slowly, their periods measured in billions of years rather than the hundreds of millions of years typical of disk stars. A gravitational perturbation that would barely be noticeable in the dense, dynamically hot inner disk can produce a clear, long-lasting signal in the cold, slow outer halo. This is why stellar streams, which predominantly inhabit the halo, are such valuable tools for mapping the distribution of dark matter. Their slowness makes them sensitive. Their long coherence times mean disturbances from the past are still visible now. New analysis of the stellar stream population, enabled by Gaia's complete dataset, and new algorithms like StarStream developed at the University of Michigan, has dramatically expanded the catalogue of known streams and revealed properties that earlier searches missed. Many of the newly identified streams are shorter, wider, or misaligned compared to what a simple gravitational model predicts. These anomalous shapes require forces that standard models of the Milky Way's mass distribution do not include. The most natural explanation is that the outer halo contains more structure, more massive, more concentrated clumps than smooth dark matter models allow. Self-interacting dark matter produces exactly this kind of additional small-scale structure. Ghost satellite galaxies add to it. The gravitational wake of the Large Magellanic Cloud complicates the outer halo's dynamics in ways that are still being fully characterized. All of these effects are operating simultaneously in the same region of the galaxy, making clean attribution of any single stream's properties to a single cause extremely difficult. What the full dataset of stream shapes, positions, and kinematics allows, when analyzed together rather than individually, is a statistical characterization of the outer halo's dark matter distribution. Rather than asking what caused this specific gap or that specific width anomaly, scientists can ask what distribution of dark matter masses and densities is consistent with the full observed population of stream properties. That statistical approach is more powerful than case-by-case analysis and less sensitive to ambiguities in individual examples. The answer coming from that analysis is not yet fully published, but the direction is clear. The outer halo of the Milky Way contains more structure at small scales than the standard smooth model predicts. Something is out there, in significant quantities, too dark to see directly and too numerous to be explained entirely by known satellite galaxies. The outer halo is crowded with invisible things in motion, and their collective gravitational influence is being read, right now, from the shapes of stellar streams spread across hundreds of thousands of light years. Every decade of astronomical observation has revised the picture of the Milky Way significantly. This decade is revising it more than most. 20 years ago, the working picture was relatively clean. The Milky Way was a large spiral galaxy with a central bulge, a rotating disk, a relatively smooth dark matter halo, and a collection of known satellite galaxies orbiting at various distances. Dark matter was understood as a gravitational scaffold, present everywhere in the halo, holding the galaxy together, but essentially passive in its behavior. Interstellar objects were theoretically expected, but had never been observed. The Andromeda collision was considered essentially certain in about 5 billion years. The galactic center hosted a confirmed supermassive black hole, whose properties were increasingly well measured. Every element of that picture has been complicated by what the past several years of observations have revealed. The dark matter halo is not smooth. It is lumpy, asymmetrical, and actively being reshaped by the Milky Way's ongoing merger history and the gravitational influence of its satellites. Its inner structure has been distorted by billions of years of collisions and may not be a discrete object at the galaxy's center, but rather a continuous gradient of density through the halo. The outer halo is populated by more clumps and subhalos than standard models predicted. The disk is rippling from a relatively recent gravitational disturbance. The satellite population is likely roughly double what current catalogs show. Dark matter itself is no longer clearly the featureless inert substance the simplest model assumes. Multiple independent observations, stream gaps requiring self-interacting clumps, a 3-signal excess at the galactic center, consistent with dark matter annihilation, disk oscillations driven by massive passing objects, all point toward a substance with internal physics. Whether that physics takes the form of self-interaction, annihilation, excited states, or some combination is not yet determined, but the data increasingly disfavors the picture of dark matter as a perfectly passive, perfectly cold, perfectly smooth gravitational fluid. The Andromeda collision is no longer certain. The certainty that was announced in 2012 has been reduced to a 50-50 probability by the most precise data available. The Large Magellanic Cloud, barely considered a significant gravitational player 2 decades ago, may be the deciding factor in whether the two largest galaxies in the local group merge or fly past each other. Interstellar objects are real and arrive regularly. They carry chemistry from other star systems. They come from different regions of the galaxy than expected. They are chemically anomalous in ways that do not fit local comet formation models. The galaxy moves material between its star systems at a rate that implies deep chemical connectivity across the entire disk. The picture that is emerging is of a galaxy that is dynamically alive, perturbed, connected, structured at every scale by forces that have been acting on it for its entire history and are still acting on it now. The Milky Way is not a stable platform that happens to exist in a quiet neighborhood. It is an active, disrupted system embedded in a larger, active, structured environment. Understanding it fully requires not just mapping its stars, but reading the invisible forces that have shaped every aspect of its structure. That reading is underway, and what it reveals, piece by piece, is that the galaxy is stranger, more complex, and more connected to its cosmic environment than any model from the previous generation of astronomy predicted. The next decade of astronomy is the most consequential period in the history of studying the Milky Way. The Vera C. Rubin Observatory's full 10-year survey will produce the deepest, widest map of the southern sky ever made, discovering new satellite galaxies, new stellar streams, new interstellar objects, and providing the statistical foundation for measuring the outer halo's dark matter structure from the shapes of the full stream population. Its data volume is unprecedented, and the scientific output will take the full decade and beyond to fully analyze. Gaia's final data release will provide the most precise kinematic map of the inner and intermediate Milky Way ever assembled. Combined with Rubin's depth for faint objects, the two datasets together will produce a complete picture of the galaxy's stellar structure and dynamics from the galactic center to several 100,000 light-years out. The dark matter distribution inferred from those dynamics will be the most detailed ever derived for any galaxy. The Square Kilometer Array's first science operations will address the galactic center excess directly by searching for the predicted population of millisecond pulsars at high sensitivity. Its result will either account for the excess through detected pulsars or leave an unexplained remainder that must come from something else, most likely dark matter. Either outcome represents a major step forward. For interstellar objects, the next decade is the window in which an interceptor mission becomes feasible if the engineering investment is made now. Rubin's detection capability means future interstellar visitors will be identified earlier in their approach, providing more lead time for mission response. Fast propulsion concepts, solar sails, nuclear thermal propulsion, and other technologies currently in development could reduce the response time from years to months. The first close study of an interstellar object's surface is within reach of this decade's technology and budget levels, if the decision to pursue it is made. Underground dark matter detectors are being upgraded to their next generation of sensitivity. If dark matter interacts with ordinary matter at rates above the new threshold, these detectors will find it. If they remain silent, the interaction cross-section of dark matter with ordinary matter will be constrained to levels so low that most conventional detector approaches become unviable. And the galactic scale observation approach, reading dark matter's properties from its gravitational effects on stars and streams, becomes the primary viable strategy. The 2005 discovery of 3I/Atlas from the direction of the galactic center, the three simultaneous unexplained signals from that center, the stream gaps requiring denser than predicted subhalos, the disturbed disk, the uncertain Andromeda trajectory, the ghost satellite population, the dark matter sheet surrounding the local group. All of these are open threads in the same investigation. The next decade of instruments will pull on each thread simultaneously. Some of those threads will resolve cleanly. Some will reveal deeper complications. Some will connect to each other in ways that are not currently obvious. The history of astronomy suggests that the most important discoveries are the ones nobody predicted, the anomalies that do not fit the current model, and resist every obvious explanation until a new framework is built to accommodate them. Several such anomalies are already present in the current dataset, sitting in the data, waiting for the right instrument or the right analysis to make sense of them. The galaxy is full of things in motion. The tools to see them are being built. From the moment the Milky Way formed, things have been moving through it. The first stars that ignited in the early universe seeded the galaxy's halo with heavy elements when they exploded. Smaller galaxies fell in, were stripped apart by tidal forces, and deposited their stars and dark matter into the growing structure. Gas clouds collapsed, formed stars, ejected comets, and some of those comets were flung out of their systems into interstellar space, beginning journeys across the galaxy that would last billions of years. Dark matter, sub-halos orbited through the halo, occasionally grazing the disk, occasionally passing so close to a satellite galaxy that they altered its internal dynamics. This has been happening for the entire history of the galaxy. It is happening now. The interstellar comet detected in 2005 was not an anomaly. It was one visible instance of a process that has been continuous for billions of years. The dark matter moving through the outer halo is not a recent development. The subhalos have been orbiting since the halo first assembled. The Andromeda approach is not a new threat. It has been in progress for the entire history of both galaxies, advancing at over 62.8 miles per second without interruption. The gravitational waves from the dark matter sheet have been channeling the motion of local galaxies since the large-scale structure of the universe first formed. What is new is our ability to see it. For most of human history, the Milky Way appeared static. The stars seemed fixed in their positions, the sky seemed permanent, the galaxy seemed to be simply there, a backdrop to human events rather than an active, evolving system. The first hints that this was wrong came with the detection of stellar motions in the 19th century, and the discovery that the galaxy was rotating in the 20th. But even those discoveries left the Milky Way seeming fundamentally settled, a structure that had arrived at its current form and was maintaining it. The past decade of observations has dismantled that picture completely. The galaxy is not settled. Its disk is rippling, its halo is lumpy and asymmetrical. Its satellite population is larger than thought and actively in motion. Its dark matter distribution bears the scars of every major collision it has experienced. A neighboring galaxy is approaching with a 50% probability of direct impact, and objects from other star systems are passing through its inner regions at a rate that implies deep, ongoing connectivity between the galaxy star systems. Every measurement that resolves one piece of this picture raises a deeper question. The stream gaps pointed to dark matter subhalos, which pointed to self-interacting dark matter, which connects to the galactic center signals, which connects to the question of what the central mass actually is, which connects to the broader dark matter distribution, which connects to the dark matter sheet, which connects to the Andromeda approach, which connects back to what all of this means for the long-term future of the galaxy and everything inside it. The thing moving through the galaxy is not one thing, it is many things. Objects, forces, invisible masses, approaching galaxies, chemical payloads carried by ancient comets, all of them in motion simultaneously, all of them connected by the gravitational architecture of a system too large and too complex to see all at once. We are inside it. We are moving with it. And we are, for the first time in the history of any species anywhere on this planet, beginning to understand what the galaxy around us is actually doing. The instruments are pointed. The data is arriving. The picture is assembling. Whatever is moving through this galaxy, we are finally learning to see it.